Time to learn some new derivative rules, in particular, the derivative of logarithmic functions. Before we find the derivative, we're going to work with a special limit. The limit is a approaches 0, 1 plus a to the 1 over a. How we're going to evaluate the limit is we're going to make ourselves a chart. We'll pick a value for a and work out the limit 1 over a. So why are we picking 1? 1 is reasonably close to 0, and it'll just give us a good idea of what we're doing. So what we're doing is plugging in the 1 everywhere there's an a. We'll get 1 plus 1 to the 1 over 1. And 1 plus 1 is 2, 2 to the 1 is 2. Let's get closer to 0. So a number closer than 1 is 0.1. Plug that in. 1 plus 0.1 to the 1 over 0.1. 1 divided by 0.1 is 10. And when you take 1.1 to the 10, you get 2.59374246. And what are we doing? We're trying to see what this is approaching as we get closer and closer to 0. So we were at 2, we're at 2.59. Maybe you might be thinking we're approaching 3. So let's check. Pick a number closer to 0, 1.01. Plug it in everywhere you see an a. So 1.01, 1 over 0.01 is 100. We get 2.7048. Now, if we're getting closer to 3, we're taking our time. So let's check another one. Get closer to 0. Plug it in and work it out. And you might be suspicious now that we're not actually approaching 3 at all. Looks like we're staying fairly close to 2.7. Let's take another one. 0.0001. Plug that in for a. 1.0001. 1 divided by 0.0001 is 10,000. What are we approaching? It turns out when you get very, very, very close to 0, the number you're approaching is 2.71828182845.9, etc., which I hope some of you recognize as E. If you don't, you can get on your calculator, find the E button, calculate e to the 1, and you'll see this number. So the limit as a approaches 0, 1 plus a to the 1 over a equals e. How is that useful? You'll find out. So we're going to determine the derivative of y equals log base b of x. Let's start with the definition. The limit as h approaches 0, f of x plus h minus f of x all over h. This is the definition of the derivative. We can use this to find the derivative of any function whatsoever. F of x in this case, y equals log base b of x. So f of x and y mean the same thing. So if y equals log base b of x, f of x equals log base b of x. Calculating f of x plus h, everywhere there's an x, we're replacing that with x plus h. So f of x plus h is log base b of x plus h. We can then put them in. Instead of f of x plus h over here, we're going to put in log base b of x plus h. And instead of f of x, we'll put in log base b of x. So this is what f of x plus h was equal to. And this is what f of x was equal to. Now, simplifying the top of this fraction, we're going to have to remember some laws of logs. When you had the log of a quotient, you could write it as the log of m minus log n, which means if you have the log of m minus log n, you can write it as the log of a quotient. So we have the log of x plus h minus the log of x. That's really the right-hand side. So we'll write it more like the left-hand side. So again, what you're doing, imagine that's your m and that's your n, and then we're writing it as log m over n. So we can write it as log base b, x plus h minus x. Let's clean this up further. The 1 over h, let's just pull it out front. And then x over x is 1. H over x will leave us h over x. So one more time, we were dividing by h. So that's really the fraction 1 over h, which we're pulling out front. And then x over x is 1, and h over x stays h over x. There's a lot happening here. a little too much for us to work this out simply. So what we're going to do is make a substitution and hope that that makes things look easier. Let's replace the h over x with a. If we do that, then x times a is going to equal h. So x times a is equal to h, so we'll be able to put that in. H over x is a. We just have to get rid of the limit now as well. So if h is going to 0, what is a doing? If h is going to 0, it looks like a is also going to 0. So your new limit, instead of h going to 0, we'll replace it with a going to 0. Instead of h, we'll use ax, so this becomes 1 over ax. And instead of h over x, we'll replace it with a. Let's look at that one more time. We replaced this with a. That allowed us to multiply both sides of the equation by x and get ax equals h, which is allowing us to get rid of this. And then we need to get rid of the limit as well, because if everything is in terms of a, it doesn't help to have a limit because h approaches 0. So if h is going to 0, a is also going to 0. So the replacement, h going to 0 became a going to 0. H was equal to ax. H over x was equal to a. How does that help? There's another law of logs that says if you're multiplying by a number, that's the same as raising this to a power. So I took the 1 over a and put it as the exponent 1 over a. The 1 over x just stayed where it was. And I'm hoping you recognize something. The limit as a gets close to 0, 1 plus a to the 1 over a. That's that limit we looked at just a minute ago, and that's equal to e. So e is going to go in here. So the limit then, as a goes to 0, that has no impact on the 1 over x, so that stays 1 over x. Log base b has to stick around. And 1 plus a to the 1 over a, as a approaches 0, is e. So our derivative is 1 over x, log base b of e, and that's it. Let's look at that again. If you have log base b of x, your derivative, 1 over x, log base b of e. Now, if anyone has looked at this online, you will have found a different version of the formula. For those who want to know why they're the same thing, keep looking at this slide. For those who don't, you can skip the slide and everything will still be all right. There's a change of base formula for logs. If you have the log of a, log base c of a, you can change that to any base you want. So our new base, just make sure you put the argument on the top and the original base on the bottom. So if we apply this rule over here, we're going to end up changing this to this expression. So our new base that we're going to pick, let's pick base e. So our new base is base e, and we put the argument on the top and the base on the bottom. New base, argument on top, base on bottom. What that does for us, what exponent goes on e to give us e? That answer is 1. And there's an abbreviation for log base e, which is ln. 1 times 1 is 1, and x times ln b is x ln b. And there is the other version of the derivative. And you might be asking yourself, how do you know which one to use? And that answer will depend entirely on where you go to school. So your professor will tend to show you one version or the other, and your textbook will tend to use one version or the other. In this class, we're going to use this version. So again, derivative of log base b of x, 1 over x, log base b of e. This is known as your argument, so we just take 1 over the argument and multiply by the log of your original base of e. Let's find some examples. Let's take the derivative of log base 10 of x. Log base 10 of x. Derivative would be 1 over x log, what was our base? And then we put the e in. So 1 over argument, log base 10 of e. Let's try another one. 7 log base 5 of x. The 7 we know is just going to get multiplied by the answer. Log base 5 of x, the only thing we're changing is the b to a 5. We get 1 over the argument, log base 5 of e. Now, there is a base that would allow us to simplify this? It's not base 10 because we can't do anything with that. It's not base 5 because we can't do anything with that. So what base could you have here that would allow you to evaluate this log? And the answer is e. Let's look at it. If we took log base e of x, the derivative 1 over x log base e of e, so 1 over x log base e of e, and what exponent goes on e to give you e? 1 does. So our derivative is suddenly looking much simpler. Derivative of log base e of x is simply 1 over the argument. What happened to this term? It's just 1 in this case. We can make this look even better. There's an abbreviation for log base e, and that's ln. So the derivative of ln x, because it is simply log base e x, is exactly what we had over here, 1 over x log whatever your base is. And we know the base is e of e. What exponent goes on e to give you e? 1 does. So the derivative of ln x is 1 over x. This is the rule that we're going to spend time working on today. The derivative of the ln of an argument is 1 over the argument. Let's try some examples. So y equals ln x squared plus 5x plus 1. The derivative of the ln of the argument is 1 over the argument. And then what's happening here? We have to keep in mind the chain rule. The chain rule will tell you to take the derivative with respect to the argument, which gives you 1 over the argument. Then we have to multiply by the derivative of the argument. So the derivative of x squared is 2x, derivative of 5x is 5, derivative of 1 is 0. And you might be saying, why did we not see this term up here in the original derivative? Well, let's try it. When you take the derivative of the ln of the argument, 1 over the argument times derivative of argument. 1 over argument, and what is the derivative of the argument? The derivative of x is just 1 in this case. And that's why it wasn't so obvious that we had the derivative of the argument here. But you remember this, and it makes perfect sense because of the chain. Let's try another one. So the rule again, when you take the derivative, you take 1 over the argument, and because of the chain rule, we then multiply by the derivative of the argument. So 1 over the argument and derivative of sine is cosine. Now, many of these fractions will clean themselves up, particularly when you work with trigonometry. So cosine over sine can be written as cotangent. Let's do another one. Now, for anyone who's saying, oh, I never really liked logs, here is your chance to like them. I'm trying to give you a question that's more complicated. At the moment, there is a chain rule involved, but because it's a log, you can use your law of logs to say, I'm allowed to bring that exponent down front. So we haven't taken a derivative. This is still y. We're simply using a law of logs to change from the exponent to multiply. How does that help? Now there's no chain rule involved with an extra exponent here. So we'll take the derivative, it'll be 5, and then we apply the new rule, which says 1 over argument times derivative of argument. So again, what do? We did the law of logs that allowed us to bring the 5 down. That's simplifying, not taking a derivative. The 5 gets multiplied by your answer. The answer for the derivative of a logarithm is 1 over the argument times the derivative of the argument. And then clean it up. 5 times 2x is 10x, and the denominator stays x squared plus 2. And again, I try and make this complicated. I'm giving you the ln of a fraction. There's a quotient rule involved in the moment. But you can use the law of logs. When you have the ln of a quotient, you can write it as the ln of x cubed plus 1 minus the ln of x cubed minus 1. And then your derivative is much simpler. So again, for those who are saying, oh, I really didn't enjoy logs, there's good reason to enjoy them here. It's very, very difficult for me to give you a question that's particularly hard because you'll just use the law of logs to change it into something easier. So again, what we did, when you have the log of a quotient, we can change it to subtraction, and then we take the derivative. The rule for logs, 1 over the argument times derivative of argument, 1 over the argument times derivative of the argument. Your job today on page 1, there's 19 questions to do. Some of them simplify in an interesting way, so if you're unsure of why the answer looks the way it does, Just let me know and I'll help explain that. Have fun.